passwords of every user. So we want the user to be able to change only his password, not somebody else's password.
So they got to have certain entries.
Yeah, so this password program has to make sure if you run this program, you can change only your address. If somebody else runs this program, they can change only their address, right? But in order to change even your own password in the password file, you need to be the root, right? Because this password file is owned by the root. Only the root can access the password file. You are a regular user. So as it is, you cannot access the password file, even if you want to change your own password. But you are not trying to access the password file by writing your own program. What you are doing, you are using the password program, and through this program you are accessing the password file, right? So that's why this password program has to be declared, has to be a special program, right? It cannot be what? If it is something that only a root can run, you cannot run this program, right? So it's a bit. So when you store all these permissions, now you know that, right? You have user permissions, group permissions, and the others, right? So you have 9 bits, right? RWX for each. So 9 bits UGO, and then the bit preceding this UGO, you really have the set user ID bit. So totally there are 10 bits. Okay? So this is typically set to 0 to indicate it is not a set UID program. But if you set it to 1, it means it is a set UID program. Okay? So if you have a program that you have and you have the UGO, all the 9 bits set, whatever you want for the RWX, and before that there's a bit, actually it is typically 0, but if you make it 1, it becomes set UID program. And for this password program, the set UID bit will be set. Only if the set UID bit is set, a regular user can access that program. Okay? So you write your program, say as a root, but you want someone else to be also able to run the program and do something. You want to make that as a set UID program. Okay? And also what is really what you want to do is, through this program, you want the normal user to actually change the contents of the password file, right? So when you make the set UID, when you make a program to be a set UID program, at the runtime, even though you are a regular user, when you run this program, you have all the privileges of the owner of this program, right? So if the owner of the program is a root, when you run the password program, you have all the privileges of the root. That's the reason why you can access the password file, because when you run the password program, you are really the root and you have access to the password file. But the program has to be carefully written, because if it's not carefully written, someone can misuse and change anything they want on the password file. So it has to be written in such a way that a particular user can still access only his particular entry on the password file. Okay, so you elevate the privileges. So you are a regular user, but you are accessing the set UID program, so your privileges are elevated to the root. Okay, but still you can do only what you are supposed to do, not change something else. You see that? So there is an elevation of privilege or escalation of privilege, but in order for someone to be not able to exploit it, that program has to be carefully written. A set UID program has to be carefully written. Okay, so that's why it is always risky to make a program as a set UID program, okay, because someone can misuse it. And coming back to this, if this is a set UID program, right, which means someone is calling, if the main function, wherever it is a set UID program, someone is calling that main function by passing command line with this harmful code and this as a string, which means it has some malicious code in it. So when they run this program, they have the privilege of the root. Alright? So which means when you go to this portion of the stack and you execute this, you run this as what? As a root. Right? Because you're running this program and this is a set UID program, so you have the privilege of the root. So if it is something like delete all the files in the system, the root can do that. If the script tells you to delete all the files will be deleted. Right? So that's why it is very risky to allow SetUID programs. Okay? And that's why you have to be very careful. Which means, as I said, you have to be very careful writing what? The SetUID programs. And what's the vulnerability over here? Use a string copy function. strcpy, very old string copy function of C, has this vulnerability. What vulnerability? It doesn't check for the overflow, because you see, you could typically override anything onto this 12-byte character array. I could overflow 100-byte information like this, or how long it is, onto this 12-byte, which means it overflows the subsequent byte. The string copy function will not check for any overflow, right? If you have, can you do this in Java?
Or you talking about for connection to check for?
Yeah, can you, this is C code, right? Can you think of some Java program where you can cause a buffer overflow like this? Have you tried in a Java program to declare an array of 12 characters long and try to write to that array more than 12 characters? What will happen?
It will overwrite.
It's going to give an error message, right? Array out of bounds or something.
Yeah. I've seen that before.
Right. Because Java is considered to be what is called memory safe language. It won't allow overflow like this. Yes.
I'm sorry to ask you, well, when I was doing taking John, what come like, let's say you got like I used to always do like, so when I do my arrays, I probably say 50 characters. And like, why come like people don't like you doing it?
Right.
Even though you're not gonna have 50 characters, I know it's gonna be but why, just to gonna say I say fast because I don't have time.
It's not a good programming.
They don't like that. My teacher didn't like that.
It's not a good programming practice. Why? Because if you want to store only 12 characters, but you're declaring an array of 1000 characters long, you are kind of committing those 1000 memory cells, right? And they are not available to any other program. Right? You are reserving those 12,000 memory cells for this character array. Actually, you need only 12 or 10, whatever it is. So that's the reason why a teacher won't like you, because they want to teach you the good programming practice.
Okay. I never knew.
Okay. All right. So Java is considered to be memory safe because all the string copy functions or any function you have in Java where you want to copy things to another thing, it won't let you to overflow an array. Okay? Whereas C, as it is, a traditional C, some functions in C are nowadays memory safe, at least in C++. But in the traditional C, like this, it's not memory safe. It will let you to overflow.
You said C++ memory safe?
C++, if you have heard of this STL, standard template library, like the built-in functions, to do the string copy and all those things, they are considered to be memory safe. Okay. There is also a string copy, strncpy. This is strcpy. There's another thing called strncpy. All it does is you have to pass the length of the string. So if you want to overwrite if you want to write only copy 10 characters, if you want to copy 20 characters, and so on. It is still not memory safe. Why? You could declare C of 12 and you could pass 20 here. What will happen? It will copy 20 characters from that and overwrite to this. So, but it's slightly better than not specifying anything, because if you are a watchful programmer, you will make sure you are not trying to copy more than the array size. So that's the reason why they added this strncpy. But it's not really making it memory safe. It's up to the programmer to make sure that it's not overwriting more than what it is.
So what does it do, Dr. Meg? If it doesn't make it memory safe, what's the purpose of it?
What's the purpose of it? It copies things. You want to copy from this bar wherever it's pointing to, from this string to this. When they developed this, probably the 70s and 80s, they didn't think of this. They thought, okay, it's overflows, you'll get a segmentation fault. But with all these attacks that started coming, someone can misuse this and pass a script that could be run at an elevated privilege, like as I said, right? And you could run, if it's a setuid program, you could really misuse it. Okay? So this is what is called a stack smashing buffer overflow attack. That's the name of this. Kind of really beating up the stack and trying to exploit it. So actually, this is very interesting thing to implement it. There's nothing more of a program-wise. You have to really watch out the memory location and things like that, and cause this attack. So I am thinking of a project on this. I have to work on this, but I tried this before. It came up well, but I have to make sure to give all the instructions and everything so that you guys can do it. So it's not a programming project, but you have to really play with it a little bit until you can really launch the attack. Why? As we'll see now, what is more important, what is very important to be successful to launch this attack? You need to be able to find this memory address. What is the starting point? Because you want to overwrite the return address with this. If you overwrite the return address with something else, you are not going to be successful, right? So you want to overwrite the return address exactly where your code starts, right? So you want to find where the return address is stored, right? This thing. Because for us, in this example, it was easy to visualize this because it's a small code, right? But imagine what an attacker will face in practice. He won't be able to see the structure of the code, right? So he won't know what are the things on the stack. But still he wants to kind of launch his attack. So he has to know where you should place the return address and what value he should place the return address. So basically he has to know the size of the stack, starting from here up to this return address point. So he has to know how large is this portion. So it's more or less a guessing game. Okay? At least when you do it as a project, you have to try it a couple of times before you can really find where the return address is. Okay? If you use a debugger, I don't know whether you have used a debugger, right? In a C context, you can actually see each memory address where each byte is stored. So you can really go to that level. If you use a debugger, you can probably be kind of successful in the first or second attempt itself, because you can easily locate where the code is there. So you can point the return address to that code and really make the program to return to that address and run that code. Okay? So it's something that is good to know if you have not used before. Okay? We'll see. It takes time for me to come up with a project on that, and then I'll give you time to do that. Okay. But at least more from an abstract point of view, how could someone launch this attack? There's a technique called NOP sliding. There are several ways to launch this attack. From a more practical point of view, this is just one way of doing it. NOP stands for what? No instruction. Huh? No instructions or no op. It means it's a dummy instruction. It doesn't do anything. Alright? So as I said, the key thing is trying to find the space. How large is the distance between the return address where it is stored and where you want to return this portion, right? Now, as a guessing game, what you have to do is you have to fill up the stack with a sequence of no-op instructions followed by the bad code or the evil code that you really want to execute, followed by the return address. Okay, so this RET actually represents this memory address. But I want to replicate it or duplicate it in all these things several times. Why? I never know where the return address is pointing to. So if I replicate it several times, my hypothesis is I will manage to overwrite it somewhere. If I write it only once, right, if I pass the code like this, if I pass the code simply, my evil code or whatever the array contents I'm passing is just like this, it may go and get stored somewhere, but it may not override the exact return address, right? Because as I said, you have to know what? The size of the stack for this function. So if you pass something that doesn't really override this return address, you cannot launch this attack, right? So if you want to be successful, you want to just duplicate the return address several places so that at some instant you can, or some memory location can override this. So that's why you are just duplicating it several times, RET, 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 and so on. Similarly, this no op instruction several places so that you return the control, all these things are the same thing. But at one point, there will be, this is where the return address is actually pointing to, and when you really manage to override the return address to this address, the control returns to this address. Okay? And you want to make sure the evil code is executed still. So you don't want to put the evil code exactly over here. You want, or somewhere, you may end up putting it above. So you want to still put some dummy instructions. So once a control returns here, start executing from here all the way down, and then you see the evil code. So the whole idea is you don't want the evil code to be outside this range. Right? So you put the dummy instructions and then the evil code and then a sequence of return address. Same return address will be extra return. And this you may have to try trial and error. Okay, you may not be able to get it right away. Okay, so you have to guess different return address because you want to basically guess the size of the stack. Okay, so that you can put your evil code somewhere and the no op instructions above that, so that you can really manage to return to that address and then execute from there. Okay, so it's called sledding. Sledding means you just go down one by one, like if you climb down a kind of staircase like thing, you just go no op, then evil code and then return address. So that's why it's called NOP sledding. Okay, because you don't really do anything with the no op instructions, you just skip those things and you the evil code. That's why it's called no op sledding. Okay? Here, it's explained also more in detail, so you can go through it. So this is how you put one way or a very classical way of launching a stacks overflow attack. Okay? So we'll see some, any question? Huh? That's what I'm trying to think of as a project, but if, how to really do it in practice. Okay, you need a debugger. If you have used a debugger, probably you guys have not used C at all, right? So, have you C?
I think I got Visual Studio still.
I don't think it's possible in a Windows environment. You have to use a Unix environment or Linux.
You have to be Unix.
Yeah, or Linux, like Ubuntu.
The Ubu. Okay.
We'll see. It's a good thing to at least know all these things and try it once. Okay, so some of the protection schemes to prevent this attack or at least detect this attack. This is actually to detect this attack. Someone is trying to because the key thing is what? Someone should be able to override the return address, right? So once only they override the return address, they will be able to return to the code, the portion where their harmful code is, right? So you should not let the return address to be overwritten, all right? So one idea is to put a random integer called a canary, okay? Since how the stack is actually growing, the stack is growing from high to low end, right? So which means if someone has to override the return address, they should override something before the return address, right? Because you are overwriting things from low to high, right? You are filling up the stack from low to high. Like, how did I do this? Harmful code, and then I overwrote this. So before I overwrote the return address, I overwrote this portion, right? So I put my canary just before the return address. Alright? So dummy variable again, so it's an integer, it's like 4 bytes. So every time I come to the return address and try to return to that address, I check the value of my canary. Okay? So actually stored, I showed in a picture over here. So every time I come to the return address, I check the value of my canary. If the canary is the same as what I had before calling a function and executing it, then I return to because it means the canary is not overwritten, right? So the canary remains the same as it was initially, then I can assume that the return address is not overwritten. If the canary value is different after I run the stack, it means while the stack was run, like for example by calling this function foo, it means someone overwrote the return address, because if the canary is overwritten, more probably the following thing, the return address is also overwritten. The canary is not overwritten, the return address is definitely not overwritten, because someone has to overwrite the canary before they can overwrite the return address, right? So if the canary is not overwritten, the return address is not overwritten. But if the canary is overwritten, more likely the return address is also overwritten. Okay? So when you check for the value of the canary and it is different from what it was initially, you kind of raise an error and don't return to that address. Okay? So that is the way you can protect the system from being attacked.
How can you check how you go about doing that?
You have to store the processor, like all these things are done by what? The processor, right? So you have to really store the value of the canary somewhere in a register and check if its value has changed. If it's not, then you can return to that address. If its value has changed, you have to stop running that program.
Okay.
Okay? Some other protection schemes are, don't let the stack to be an executable stack. The whole problem comes if whatever the code I can store, the shell script, is allowed to be executed from the stack, right? So you want to allow code to be executed from the stack for more use of this program. Say for example, if I want to run something from the stack as a genuine user, I should be able to do it. But if someone can misuse it and pass a script, a malicious script and run it, it's a misuse, right? So if you want to avoid someone from misusing it, just make the stack non-executable, which means you cannot run any code from the stack. Okay? So that's what I mean by making the stack non-executable. But a genuine user also loses the functionality by doing that. Okay? So even if you make the stack non-executable, someone can still launch the attack by doing what? They can target the heap. Remember, going back to the process address space, the stack grows like this, right? So if you make the stack non-executable, I can go, for example, even do the NOP sledding, and I can put my evil code somewhere in the heap. And the heap, if it's executable, I can return to that address in the heap and execute my evil code, right? So all you have to be an attacker from an attacker point of view, all you have to be able to do is manage to put the code somewhere you can execute, all right? So if you manage to put the evil code in the heap and if it's executable, all you have to do is return to that address and execute the code there, all right? So yes, you can make the stack non-executable, but an attacker can, if he can manage to put it in the heap, yes, he can still be successful. Okay? So what is preferred? Instead of doing all these things, it's always preferred to use what? To do what? Bounce changing. So the programming language itself has to be memory safe. That's very preferable, like C# and Java and all of memory safe languages. Otherwise, you have to write a program, like make sure, like for example, instead of calling string copy as it is, write your own string copy function that checks all these boundary things, makes sure there's no overflow, and then copies things. Okay? So for example, you can write your own string copy that you will use this string copy, but before calling the string copy, you can write, for example, I can write customized string copy that gets the C and bar, but I make sure the length of the bar is what? Less than the length of the array C, right? Whatever I want to copy it to. So after I make sure the length of the string that I want to copy is less than the length of the character array, I can call the string copy function, the built-in string copy function. But what you have to do is you have to write your own customized string copy that calls the built-in string copy by doing this boundary checking. So this is actually a good programming practice, okay? Because if you fail to do that and you're writing a C program like this, it's vulnerable to be attacked. Okay? So that's why in C and C++, the new library functions, the standard template library functions are memory safe, because once people have tried these things and successful, they kind of enhance the C++ library to have new functions that are memory safe. So that someone cannot really launch all these things. Okay? Alright? Any question? So I have to go through it one more time to make sure you get it. Okay? That's why I want everyone to be here today. Buffer overflow to the web. So the same thing, remember the set UID thing. Okay? So, for example, you are writing a web application, and let's say the program, the user interface takes up, say, a phone number and what else? The date. Okay, so let's say, and we have seen this is what there are two ways, right? HTTP GET and what is that? If you want to make the parameters values visible to a user, post and get, right? Right. So this is called the get. The post is more secure in the sense that the values of the parameters won't be displayed along with the URL. Okay? But let's say the values are displayed, the parameter value is displayed along the URL when you're entering those values and clicking that function, and the website gets called, the program on the server side. The attacker can really see that the value of, say, the phone number is getting passed. Okay? But if you are writing a web program at the server side that can be really used by users all over the world, right? You want to make sure the phone number field that you are allocating can accommodate every country, right? So in US it is what? 9 digits. Whereas in some other country it may be 12 digits. Another country may have 20-digit phone number. Similarly, the date format. We use this format in some country, another country may use different format, right? So the size of the variables that you allocate for each of the parameters, right, has to be large enough to accommodate everyone, right? Every possible values. And if someone knows that, for example, a phone number is going to be 20 characters long, and that 20 characters is sufficient enough to accommodate a small shell script, then they can launch this attack, right? So you want to make the phone number field or any field to be sufficiently large to accommodate possible values of phone numbers from anywhere of the point, any country in the world, right? But if someone can find out that the phone number field is as long as 30 fields, that's another problem. If you declare your character array to be 1000 characters long, even though you don't need it, someone can find it out and pass a sufficiently long shell script that can fit into 1000 characters. And if program runs this value, runs the input parameters that you pass as a what? Root, then you are running that shell script too as a root, right? So you don't want to be giving the leeway for the attacker to pass the shell script to this command line or these parameters. They are allocating more than the required size. Is that clear now?
Yes.
So you have to be watchful, or at least use the post method or all those things to at least not make it very visible for an attacker. Okay? Otherwise, they can easily find out what is the large maximum size that they can use for every parameter in your form, the web page. Right? So this is what I want to say by buffer overflow to the web. So again, if on the server side, if all these parameters are run at the root or the administrator privilege, then if you could pass a shell script, then that script will be executed at the server side with the root privilege, and that could cause some harm. Okay, so that's why you should be very careful in coming up with size values for all these fields. Even though it looks simple, right? A phone number that can locate, like as you said, 1,000 characters, but you see the vulnerability associated with it.